My name is Steve Miller. I'm a math professor at Williams College, and we're going to be talking to you about how to attack problems. So this is another lecture in the coronavirus series. And the goal of today is when you're given a problem, how can you try to come up with a way that will help you find the solution? What we're going to be looking at today is a bridge problem. And one way to attack it is trial and error. Just try a couple of things and see if something works. If there aren't that many solutions, this isn't a bad approach. Or if you can easily write down all the things to try, it's not a bad approach. But as the problems get harder and harder and harder, as they get more and more complicated, the danger is you might miss the solution. When you go through, what if you don't capture every case? And for some of these problems, it's something a little bit non-standard, a little bit tricky, which is the solution. Unless you're very likely to miss them. So what we're going to do today, and then we'll follow it up in tomorrow's lecture, is to talk about how to search exhaustively. What does this mean? It means you cover every possible case. Now, for this problem, it's not going to be so bad, and we can just do it by hand. But for other problems, it's going to be much worse. There's going to be thousands or tens of thousands or hundreds of thousands or even millions of cases. What would we use for something like that?
Computer.
A computer. Computers, I won't say they love doing it because they don't really show emotion, but the computers don't seem to complain, and they can do millions of cases in almost no time. That's right.
That's because what?
They don't show emotion. So here's the we'll cross that bridge problem updated for the situation we are now living in. So we have a rickety old bridge. It's nighttime and it's dark. We have one flashlight and we've been chased by zombies or coronavirus victims. And they are 17.5 minutes away from us. Only 2 people can cross the bridge at a time. And if you're crossing, you must have the flashlight. So 2 can go across with the flashlight, and then 1 can return with the flashlight. You must get all people across before the attackers arrive. Okay, so don't go and don't yell at the solution. We're going to go slowly to get to the solution. Amazingly, the 4 people are named 1, 2, 5, and 10. Somehow their parents knew that they would be eventually facing this problem, and their names are actually how long it takes them to cross the bridge. So if 2 was going by herself, it would take her 2 minutes. If 5 was going by himself, it would take him 5 minutes. If 2 people go over together, then the time it takes the 2 of them is the longer of the 2 times. So if 2 and 5 go over together, how long will it take them?
5 minutes.
5 minutes. And then we have to get everybody across before the zombies or the coronavirus victims come over. And so if we ever have 3 people going over the bridge will collapse.
We all die.
And we all die. So the first question is it possible to get 4 people over in 17 minutes and survive?
Yeah.
Yeah, given that we're talking about this problem, there's probably a solution. Or if there isn't a solution, there's maybe a good math idea behind why there isn't a solution. And so again, if we don't get anybody over in 17 minutes, somebody's going to touch the bridge and infect it, and we will all die, or the bridge will be destroyed. So what I want you to do now is stop and pause this video and think about how you might approach this problem. How might you try to find a solution?
By the way, you can't throw the flashlight back.
That's right. You can't throw the flashlight back. The flashlight has to be walked back. So pause it now.
Why would they run? Maybe they are running.
Okay, welcome back. So how should we attack the problem? Well, one natural approach is to try some combinations, explore, try some options, and build intuition. Who would you like walking whenever possible?
1.
1.
Or 2.
Or 2. But if you had to choose a person, who would you choose?
1.
1. So why don't we say, whenever possible, 1 walks, and let's see how that goes. Okay, so maybe the fastest person walk as much as possible. Let's try that. So pause the video and try to figure out what would happen if 1 walks whenever possible. Welcome back. All right, so did you try figuring out what would happen if 1 is always walking? So you'd have to send 1 and 10 over, and then send 1 back, and then send 1 and 5 over, and then send 1 back, and then send 1 and 2 over. We're done. So how long did that take?
Long.
How long?
So 10, 11,
11,
16,
17, 19. So unfortunately, it took 19 minutes and we failed and we are all dead. So it wasn't a bad thing to try, send the fastest person over, use the fastest person whenever possible, but it didn't work. And we could try lots of other cases. We could try other approaches and see if anything works if we luck out. What I want to do is I want to do a methodical way, making sure we don't miss anything. So the question is, how can we do that? So pause the video now to think about this problem. So I'm going to pause it now. All right, welcome back. And so the question is, how can we methodically go through all possibilities, making sure we don't miss anything?
So I might start off with sharing one with each person, like in a different problem. So I would have 1 in 10, 1 in 2, and 1 in 5.
Right, so I might go 1 in 2, 1 in 5, 1 in 10 in that order.
And then I would do 2 in 1, 2 in 5, and 2 in 10. 5 in 1, 5 in 2, 5 in 10, 10 in 1, 10
Right.
in 2.
Right, so looking at all the possible first moves. And so what we want to do is we want to have a good notation so that we can keep track of who's moving back and forth. So we want to come up with, how do we want to represent the different states of the problem? So again, this is a good place to pause the video and think about how you might represent the different states. So I will pause the video for a second. All right, welcome back. And so we're talking about how would we come up with good notation. And so here's some things we need to think about. As people are moving back and forth, what do we want to keep track of? We want to keep track of who's on the starting side of the bridge. We want to keep track of who made it to the other side of the bridge. We want to keep track of where is the flashlight. And we also want to keep track of how much time has passed.
Because that will tell us.
Because that will tell us.
The
Right.
zombies are.
And in fact, as soon as the time gets too large, we know we don't even have to worry about that path anymore. So the first three are the ones that are more important. We'll be able to figure out the time from good notation for the first three. And so here, I'm going to introduce some notation. So A, B, C, F / D means people A, B, and C are on the start side, and they have the flashlight, and person D is on the end side without the flashlight. So if I write 1, 2, 10, F, 5, that means 1, 2, and 10 are still on the initial side, and they have the flashlight, and 5 is on the other side. So how many states are there? How many different configurations do we have? So any thoughts?
I don't know.
Yeah, like how many different ways can I write something like this? How many choices do I have for where person A is?
2.
2. And for person B,
2.
and person C,
2.
and person D,
2.
and where the flashlight is.
2.
So what happens? So how many possibilities are there if there's 2 for each?
10.
So why would you
Oh,
add them? Is it adding, or what do we do?
Multiply.
We multiply.
Yeah.
So if there's 2 choices for
2 to the
each,
5.
it's 2 to the 5, which is?
I don't know. It's like 32.
It's 32. So there are 32 possibilities. Now, some of the possibilities won't happen. We can't have A, B, C, D on one side and the flashlight on the other, right?
Unless we're really.
But we know that there's at most 32 possibilities. So we could go through. We could go through all of these possibilities, and the question is, how would we visually represent this? So again, I'm going to ask you to just pause the video for a moment and think about how you might want to represent it. And so I will pause the video. All right, welcome back. So we are resuming. And so we're talking about how would we want to visualize this. And so one good way to visualize this is to draw a graph. And so we're going to start here with the first node, 1, 2, 5, 10 flashlight, is everybody's on the start side and they have the flashlight and nobody's on the other. And then as was remarked earlier, the first possible moves is 1 and 2 can cross, 1 and 5 can cross, 1 and 10 can cross, 2 and 5 can cross, 2 and 10 can cross, or 5 and 10 can cross. And what I could do is I could write on these lines how long it took. So this would be how long? 2, and this would be 5 because it's 1 and 5, it's a longer one. And then what I can do is I can then look at each of these and see how could they move. And so I have 5 and 10 here, and 1 and 2 have the flashlight. So maybe 2 comes back, in which case I would go here. Or maybe I have 1, 5, 2, and 10, and maybe I send 10 backwards, which is probably a really bad idea because that took 10 minutes, 20 minutes total.
And
But
you've already lost.
so we could prune some of these possibilities, but I could list all the possibilities like this. So we can put little numbers to indicate how long each of these is, and as we just go more and more levels, we can see every time we do this, the first time we get one person here, we would do it again, we would have 2 people, and then the next time both people would move over and we would finish. So we can record the time on the lines, but it's going to be a big graph to do. We can make it a little bit shorter and more concise. So let's think a little bit. How can we trim it down? Well, can we somehow compress a little bit of this so it's not taking up as much space? Because look, we went from here to here, and then we have to go to one of these states. Let's combine this as to one giant move. You start here, and you end up in one of these states. So how could we do that a little bit faster? Went the wrong way. So how do we go a little bit faster? Well, every move has someone go from the start side with the flashlight to the end side, and then someone from the end side comes back with the flashlight. Let's just call that whole cycle a move. So we're collapsing things. So we have exactly 3 moves, and we just need to keep track of what can go where. So this is going to make the tree much smaller. It's going to cut down on the things to check. In fact, we don't even need to keep track of where the flashlight is, because we know at the end of a move, unless it's the final move, the flashlight has to return to the start. And so now we start off with 1, 2, 5, 10, and then one of them goes to the other side. And then over here, one of the people goes to the other side. And then both of the people who are left come over. So we're not showing all the possible moves now because there'll be so many lines coming through. I'm just showing, here are the moves from the initial state to the first move. I'm just showing the moves from this state, and I'm just showing the move from this state. What's nice is all of these moves here, where do they all have to end up? At the bottom. You know, I have 1 and 2 with the flashlight here, though they just move over and we're done. So the hard part is, which of these first 4 moves do I want to go to? And then from these, which of the 6 ones here do we want to go to? Now, if we think about it, there's many ways to do some of these moves. I can set up with 1, 2, 5 and the flashlight and 10 on the right. I can send 2 and 5 over, and then I can send 2 back. So how long is that going to take? It takes 5 minutes to send 2 and 5 over, and then it takes 2 minutes to send back. So that's 7 minutes. Or I could send 1 and 5 over and 1 back. How long does that take?
5 minutes. I mean 6 minutes.
6 minutes. So let's make a rule that we're not stupid. Okay? So what we're going to do is, whenever possible, if there are 2 ways to do something, we'll always do the one with the smallest time. So for these, we'll just keep track of what's the smallest way. So what's the smallest way if you go from 1, 2, 5, 10 to 1, 2, 5, 10?
We send 1 and 10.
We send 1 and 10 over, and who comes back?
1
and 1. So that would take 11 minutes. What's the fastest way to go from 1, 2, 5, 10 to 1, 5, 10, 2?
We send 1 and 2.
We send 1 and 2 over, and then we send 1 back.
So that takes 3 minutes.
So it takes 3 minutes.
Wait,
And so that's a much better way of doing this. And so we've cut it down to there's exactly 3 moves. Did I go the right direction? That went the wrong direction. So over here, this is the fastest way to get there. So 11 minutes. 15 minutes. Which of these numbers looks like it's probably a bad path? Yeah, the 11 minutes looks like it's probably bad. We only have 17 minutes. We've already taken up 11 here.
We have 6.
And so,
Well, we have 6 minutes, and the combined total of 5 to 5 over and 2 back. That's 7 minutes.
Right. So getting 5 over there is going to add up another 5 minutes, and at least 1 minute to send somebody back is 6 minutes, and then we have 2. So we can see.
Wait, isn't that 4?
No, because
No, because
you said
1 and 2 went over,
Yeah.
and 2 came back.
Yeah.
That's 3 minutes. Oh no, that's right. That should be 4 minutes. That is a typo. So we will quickly fix that. All right, we have now fixed the slide. We are going back, and we see that this one should be 4 minutes. And we've just seen that since it takes us 11 minutes to get here, there's going to be no way to make this path work. So we actually don't even have to continue calculating what's coming from these paths over here because they took too long. We might even be worried about the 6 over here. Okay, so there's already a lot of information by writing it here. So this is a really good point to remark on, that when you're doing this methodical approach, you can actually stop and you don't have to fill everything out. Now, if you're writing a computer program, it might be easier to just have the computer do everything, but we can just stop. All right, so now if you actually go through all the possibilities, here is the first solution. We send to here. So how's the fastest way to get from 1, 2, 5, 10 in the flashlight to 1, 5, 10 in the flashlight and 2 over here?
One.
One
You said
and
one and
two.
two, and one goes back.
And one comes back is 3 minutes. And now we send 5 and 10 over and send 2 back, and it's going to cost us 12 minutes. And then we send 1 and 2 over, and we're done. All right,
How much
and
time
now
is that to?
the other solution here is we send 4 over, actually we send 1 and 2 over, and we send 2 back. We then send 5 and 10 over, and then we send 1 and 2 back. And notice that both
No,
solutions,
send one back
one and-
and then one and two.
we send 1 back and then 1 and 2. Both solutions involved 5 and 10 traveling together. So let's talk about how we might attack this
And
theoretically. And 1 and 2
together.
traveling together at one point. So we have some valuable information in the problem. We are telling you that the goal is to do 17 minutes. It would be much harder if we didn't know the minimum time. If we didn't know the minimum time when we had this lengthy thing over here, well, we might actually consider maybe that is the best. Maybe that is what we need to do. But we know it's too large because we were given the information that the goal is 17 minutes and we think we can do it. We know there's 3 moves. 2 go over and 1 returns. Now we have 3 at the start side and 1 at the end side. Then 2 more go over and 1 returns. So we have 2 at the start side and 1 at the inside. And then the remaining 2 people go over, all 4 at the inside, and now we're done. So what do we know about 5 and 10? So I will let you stop and think for a few seconds, but what do you know about how they must move? Yes, what do we know about 5 and 10?
Well, you have to have them go together because they're the 2 slowest.
Okay.
And so by putting 5 and 10 together, it will only take up 10 minutes instead of 15 if you do them separately.
Right.
Which means, but you have to have somebody on the other side ready to go, because that way, if you have 1 or 2 on the other side, you don't have to send, say, 5 back.
Right, so this is a good logic approach.
So
Yes?
5 and 10 can't be the first one because otherwise you're going to take up 15 minutes.
No,
Good.
you can look at it as you're going to take up
Yeah.
20 minutes.
Yep.
Because that 5 has to come back.
And then he has to go back over again. So we know that it's probably a good idea for 5 and 10 to walk together. It's a stupid idea to have them walk initially because they're going to take up a
They're
tremendous
going
amount
to
of
take up
time.
20 minutes by themselves if they walk.
So,
You need someone. You
so-
need 1 or 2 over there to bring
so-
the flashlight back.
if they're on separate trips, that's at least 15 minutes. So we know that there's going to be trouble. So we can solve this problem theoretically. We can solve it without enumerating all the cases. By just doing a little bit of analysis, we figure probably send 1 and 2 over, and then try sending 1 back, try sending 2 back, see if either works. And then that will lead us to a solution. So I'm going to end with a problem for tomorrow. So young Saul, a budding mathematician and printer, is making himself a fake ID. And I would like to publicly state that neither I nor my assistants condone making fake IDs or using fake IDs.
We don't.
We don't.
We don't.
We don't.
Are
Two
you
out of
sure?
That may
two out
not
of
be
2 out of 3 of us.
100%.
2 out of 3 of us do not condone
Wait,
using fake
I was
IDs. All right,
asking a question.
all right.
I said
So
we
here-
don't.
I mean, that's
Okay.
not completely
All right.
true.
Here's the problem, okay? He has the symbols 1, 5, 6, and 7. He has 1 of each, and he has an unlimited supply of plus, minus, times, and divide, adding, subtracting, multiplying, and dividing. So using each number exactly once, but you can use any number of plus signs, any number of minus signs, any number of times, any number of divides, how can you get 21 from 1, 5, 6, and 7? So you can't do things like 15 plus 6 equals 21. We're not allowing you to combine things like that. You have to use a binary operation. So we could do 1 plus 5 times 6 plus 7. How much would that be?
So 6 times 6 is 36.
Plus 7 is
40.
43. So it would be really bad to do 1 plus 5 times 6 plus 7. But this hopefully is a little bit harder than the bridge problem for you. And it's not quite clear how to attack this and make sure you don't miss anything. So I wish you luck, and we will see you tomorrow. Be healthy. And thanks again to the Journal of Number Theory and the teachers of Scholars Program who have helped us with this.